concave up is like that. Up like a cup, and concave down is like this. Down like a frown. Very good. Up like a cup and down like a frown. All right, so I am going to tell you, I want you to put dots at x equal -1, x equal 2, and x equal 2, and x equals 0. Okay, so I am concave up from -infinity till where? Good, -1. And I still, when I'm discussing the intervals where I'm concave up or concave down, or the graph is, not me, you're still talking about the x intervals. All right, and then it's subtle, but between -1 and 0, what do you think? Down. And then between 0 and 1 and 2, we're concave up again. And between 2 and infinity, we're concave down. Up like a cup, down like a frown. Easy as 1, 2, 3. All right, let's say that f is differentiable on some open interval. Then the graph is concave up if f prime is increasing. And f is concave down if f prime is decreasing. Okay, now that's kind of we're talking about f, we're talking about f prime, we're talking about concave up, concave down. That's a lot of things. So let's kind of back up a little bit. If f prime is increasing, then what do you think f double prime is doing? Double increasing? I heard it. Go back to f. If f is increasing, what is f prime doing? It's positive, okay? So anytime if something is increasing, its derivative is always positive. It doesn't matter what's increasing and like what derivative it is that's actually increasing, but the next derivative would be positive. So if f prime is increasing, then f double prime is, and instead of writing positive, I'm going to write greater than 0. And if f prime is decreasing, then f double prime is less than 0. So when f double prime of x is greater than 0, f of x is going to be concave up, right, because it just said that f is concave up if f prime is increasing. Well, f prime increasing means f double prime greater than 0. And f double prime of x f double prime of x is less than 0, then f of x is concave down. Yes. Eventually, we're going to talk about it all together. But there are times, like the whole interval from -infinity to -1 is concave up, but part of it's increasing and part of it's decreasing. So you don't necessarily have to be just increasing or decreasing. Right. Right, half the second derivative. Or, right, half of the first derivative is positive and half of the second derivative.
So would that be the same for f double prime?
No, because we're talking about where f prime is increasing and decreasing, not where f prime is positive and negative. Hold that thought. Okay, so those are the two that you need to know. So far, if f prime is positive, what is f doing? Increasing. If f prime is positive, f is increasing. If f double prime is positive, then f is concave up. So first derivative, increasing, second derivative, concave up. Okay, hold that thought for just a minute. All right, if f is concave down, then the tangent line, is it going to lie above or below the graph of f? Above. Good. If you have something that's concave down, then a tangent line is going to lie above the graph of f. Oh, if f is concave up, then the tangent line will lie below. And if f is concave down, the tangent line lies above. Sorry. That is something that I usually have to draw. I have trouble memorizing that, so I just think, okay, concave up like a cup, draw a tangent line, and it's down below. All right, so this brings up the test for concavity. If your second derivative is greater than 0, then f is concave up. If your second derivative is less than 0, then f is concave down. We're going to do this exactly the same way that we did increasing and decreasing, but we're just going to be using the second derivative. So you must first locate the x values at which f double prime equals 0 or is undefined. So for increasing and decreasing, we set the first derivative equal to 0 or found where it was undefined. For concavity, we do the second derivative. So really, you know how to do this because you know how to do increasing and decreasing. We're just going to use the second derivative. But in order to find the second derivative, you have to find the first derivative. So what would the first derivative be? Times 2x. Good. Now, anytime you're trying to take another derivative, we need to simplify this, or at least rewrite it. So I'm going to write this as negative 12x times x squared plus 3 to the negative 2. Everybody okay with that? All right, now what rule are we going to have to use? Chain rule and product. I picked the nastiest one I could find for the notes, so that you'll think the homework is easier. All right, the derivative of the first is negative 12 times the second plus the first one is negative 12x. And the derivative of the second is negative 2 x squared plus 3 to the negative 3 times 2x. Okay, I'm going to clean this second part up. I've got negative 12x times negative 2 times 2x, which is 48x squared. X squared plus 3 to the negative 3. And I need to find where this derivative equals 0 or where it's undefined. Now, we're going to factor. So between negative 12 and 48, I definitely have a common factor of 12. Or negative 12. Would you rather do negative or positive? Negative. Okay. I heard negative first. We'll do negative 12. And then what's the smallest exponent on x squared plus 3? Negative 3. So the negative 12 is gone from the first time. If I factor out an x squared plus 3 to the negative 3, what am I left with? That's x squared plus 3 to the first, or just x squared plus 3. Minus, thank you, because I factored out a negative 12, 4x squared. Yes. All right, I'm going to now write this as negative 12, and then I'm going to put the x squared plus 3 to the third on the bottom. And then that bracket is 3 minus 3x squared? Okay, I do have a variable in the bottom. What value of x will make that denominator equal to 0? Nothing. Good. So I am being kind of nice to you. If you take a number and square it plus any number, a number squared is either going to be 0 or positive. So 0 or a positive number plus 3 will never equal 0. Remember that when a fraction equals 0, so I have no points where the second derivative is undefined. And when I have a fraction that equals 0, what part can I just set equal to 0? The top. Because I can think of this as 0 divided by 1, and if you cross multiply, then you get negative 12 times 3 minus x squared equals 0. Gray? I could have done that. Yeah. Oh, 3 minus. Well, because if you did 0 over 1,000, then you would get negative 12,000 times this equals 0. And you can divide both sides by 1,000. And 0 divided by 1,000 is 0. Yeah. Right. Okay, so when I set the numerator equal to 0, I divide both sides by negative 12, and I just get 3 minus 3x squared equals 0, or 3x squared equals 3, or x squared equals 1, or x equals plus or minus 1. Do not forget the plus or minus. Okay, that's a number line. It's supposed to be straight. Now, for concavity, I'm interested in where the second derivative is positive or negative. So my number line with the zeros of my second derivative, I'm going to plug those test points back up into the second derivative. And really, I could just look at this part right here. Because no matter what I plug in for x, won't the bottom be positive? So I could just look at this top part right here. So if I plug in, say, a negative 2, I am going to get a negative times a negative, which is positive. If I plug in a 0, I'm going to get negative 12 times 3, which is negative. And if I plug in a 2, I'm going to get a negative times a negative, which is positive. No, you can't do it on the x squared equals 1 because you want it to be on the part that it equals 0 because you want to know if this part is positive or negative. You could do x squared minus 1 equals 0. Yeah. If you wanted to plug into x squared minus 1 equals 0 and use the x squared minus 1 to test your points, you could have done that too. All right, so where are we concave up? Negative infinity to negative 1 and 1 to infinity because f double prime of x is greater than 0. And I am concave down from negative 1 to positive 1 because f double prime of x is less than 0.